So we recently talked about the exponential function e to the x, and we talked about its derivative, its inverse function, the natural log of x, and I thought this would be a good opportunity for the bonus video this week to talk about a new class of functions called the hyperbolic functions. Those of you guys that are in STEM, these functions will not leave you, so now is the time for us to sort of discuss them. These are some of my favorite, this is one of my favorite parts of calculus as well, so I'm excited for this video. Hyperbolic functions are useful because they describe the natural growth geometry of growth, curvature and equilibrium in ways that like ordinary trig functions cannot do. Sine and cosine often fall short. Sine and cosine model circular motion. These functions, cosh, this is read as cosh and this is read as sinh. So sinh and cosh model hyperbolic geometry, the geometry of exponential sort of stretching. For example, this one's famous. This cosh of x is famous because if I were to have two poles, let me use blue here. If I were to have two poles and hang a chain from the two poles, that shape that's made is called a catenary, and it's modeled by this function right here, cosh of x. Engineers use this chain all of the time to design suspension bridges and power lines, so they have to get very familiar with this cosh of x. For instance, these functions show up in physics all the time as well. They solve differential equations governing things like heat flow, so our guy Fourier is very familiar with these, and also like things like wave propagation. And in fact, people like Einstein are very familiar with these hyperbolic functions. In special relativity, sort of the angle of space-time, which is called rapidity, is really measured using these hyperbolic functions. So understanding space-time means that you also have to understand these hyperbolic functions. And that is a moment when you get that far in physics, you'll understand that the typical sine and cosine don't work, whereas these two functions kind of come in to save the day, to save space-time. In fact, simple differential equations, whatever the heck a differential equation is, naturally produce these guys as solutions. So to summarize, whenever growth and curvature interact, for instance, like bridges, cables, temperature distributions, relativistic motion, like in space-time and special relativity, hyperbolic functions quietly appear as like really the language of that sort of system. So what are these things? I'm going to give a little bit of a geometric definition and then a lot more of an analytical definition. And then we'll just do like a quick introduction about the functions, their derivatives, maybe a few identities, some analogies between these functions and their trigonometric counterparts. So I'm just going to start talking about these guys. So indeed, they are called hyperbolic functions because they are related to the hyperbola. So let's imagine I have a hyperbola. Give me 1 second. Looks like this. X squared minus y squared is equal to 1. What that's going to be, it's going to look something like this. Hopefully you remember this from pre-calculus. Looks something like this. It's got these two branches. So that's what this curve looks like. Notice that this is similar to the development of the typical trigonometric functions. Those functions look something like this. We have x squared plus y squared is equal to 1. This is called the unit circle. And we have some sort of parameter. And we have the unit circle. Okay, quick sketch. If I were to go some sort of angle theta right here, then this value, so this y value, x comma y, is by definition the cosine of that theta value, comma the sine of that theta value. In other words, this theta value is the parameter for creating these cosine and these trigonometric functions, circular trigonometric functions. There is a similar sort of parameter over in this world. Oh, also, I don't know if you remember, if you notice that if I simply replace the x squared and y squareds in this equation, course, we get the famous Pythagorean identity, cosine squared plus sine squared is equal to 1, always. There's indeed an analogy over here in the hyperbolic world. But to define the hyperbolic functions, I want to, let's say I choose a point on this line. So here's some point x comma y that lives on my curve. So this is, again, x squared minus y squared equals 1. And I say that, I don't know, this area, I'm just coming up with something random. Let's say this has area equal to 3. Then, by definition, this point that causes that area to equal 3 is equal to the cosh, C-O-S-H, of twice that area, which is 6, comma, the sinh, sinh of twice that area, which is 6. Okay, so in other words, to make it more, let's say, arbitrary, I think it's super pouring outside where I'm at right now. So if this is a halves, if this area was a halves, a equals a over 2, then this point right here, or here, maybe let me do it like this. If this red area was a over 2, then this point, this other x comma y, would be, by definition, the cosh of a, comma, the sinh of a. All right, so that's like a geometric definition of these guys. And indeed, since these are points on this unit hyperbola, that's what this is called, unit hyperbola, we have our first fundamental relationship between cosh and sinh. This is almost through definition, this geometric definition. We have the cosh of x squared. Using x and y is kind of horrible, so I'll use a. Even though it's just a symbol, but x has a different meaning in this case. So cosh of a squared plus the sinh of a squared. I said plus. That's not what I want. I want minus. I'm so used to trigonometry on the brain. Minus sinh of a squared is equal to 1. So here's our first fundamental relationship between cosh and sinh. All right, so that is a geometric definition, but I actually wanted to develop a little bit more of an analytical definition, and it comes straight from our friend, the exponential function. But before I do that, I wanted to talk about what it means for a function to be odd. A function is, I want to talk about what it means for a function to be even and what it means for a function to be odd. A function is even if f of x is equal to f of negative x for each x. Technically for each x in the domain of the function. A function is odd if f of negative x is equal to negative f of x for each x. Okay, graphically speaking, hopefully this is a review for everybody, but graphically speaking, even functions can be flipped over the y-axis and land back on themselves. So maybe something like this. If you flip this over the y-axis, it should land back on itself. So even functions are preserved through reflection, where odd functions are preserved through a pi radian rotation, something like this. So this is an odd function. Here's an even function. Here's an odd function. Notice that if I rotate this, like sort of like this, 180 degrees, then it's going to land back on itself, which means that graphically it's an odd function. But this is the definition of what an even function and an odd function is. turns out you can grab any function and break it up into its even part and its odd part. Check this out. I thought this was quite genius. By definition, the odd part, or excuse me, I'll start with the even part. The even part of a function x is equal to f of x plus f of negative x, all divided by 2. Okay, so that is the even part of the function. Notice this. F of x, or I'll do it like this. F of negative x, excuse me, f even of negative x. If it's going to be well named, then by definition of even, when I evaluate this, it should just give me f of x, or f even of x at the end. So let's see what this equals. Well, this is going to equal f of negative x plus f of negative x, all divided by 2. Again, all I did was I replaced each of these x's with negative x. And then look what happens. Well, that's the same thing as f of negative x plus f of x, all divided by 2. Oh, but shoot, that's the same thing up to the commutative property in the numerator right here. That is f even. So, guess what? It's a good name. F even is even. Okay, so the even part of a random function f, so there's nothing special about this function. So I should say something like this. Let f be a function. And we just grabbed the even part of that function. There is an odd part. F odd of x is equal to f of x minus f of negative x. And let's see if this works. Then, so if we were to kind of dissect f odd of negative x, by definition, hopefully, a function is odd if f of negative x is equal to negative f of x. So this hopefully is equal to negative f odd of x. Let's find out. So we have f of negative x minus f of negative x, all divided by 2. This is equal to f of negative x minus f of x. 2 negatives cancel. Oh, shoot, but that's not quite f odd of x. These two things are in the opposite direction. So what I can do is factor out a negative. That's negative f of x minus f of negative x, all divided by 2. Oh, but shoot, that is just the negative of f odd of x. And check it out. The odd part of our function f, notice there's nothing special about the function here. The function's not doing any of the lifting here. This is strictly the relationship of this new part of the function. The odd part of f is odd. Okay, so we have these two definitions, f even, f odd, and hopefully we can show that if we sum these two functions, this is the even part of the function, that's the odd part of the function. What we're about to show is that if we sum the even part and the odd part, we should get the function itself. So let's see. So last observation, notice, if I have f even of x plus f odd of x, that is going to equal, hopefully it equals just f of x. So let's find out. F even, this is just going to be this thing, I'm plopping it down, f of x plus f of negative x, all divided by 2, plus f odd, so that's going to be f of x minus f of negative x, all divided by 2. So this is the same thing. We already have common denominators. That's going to be 2 times f of x divided by 2. Oh, wow, what magic. That is f of x. So indeed, the even part plus the odd part is equal to the function itself. So this is true for an arbitrary function. Like, I don't care what function you give me. We can write out the even part and the odd part. Let's do this for a particular function. In particular, e to the x. I'll use this color. E to the x can be written as, I'll write it like this. This is a little bit cringy, but e even of x plus e odd of x. But we have formulas for each of these pieces. We know what e even looks like. E even is going to be e to the x plus e to the negative x, all divided by 2. So again, that's the definition of our even function right here. All right. E odd of x is going to be e to the x minus e to the negative x, all divided by 2. And here's the big hoorah. This is, by definition, the cosh of x. By definition, that is the hyperbolic cosine of x. And this is, by definition, the hyperbolic sine of x. Okay, so overall, we just found our official definitions. Cosh of x is equal to e to the x plus e to the negative x, all divided by 2. The sinh of x is equal to, by definition, e to the x minus e to the negative x, all divided by 2. Immediate observations. Cosh of x is odd, or excuse me, is even. That's an even function, like by definition. This is an odd function, like by definition. Okay? And if we add these two functions, they should simply equal our great friend, the exponential. And that's really, and they do by definition. Something else we want to show, we want to kind of bring this back to make sure that it relates back to our graphical definition. In particular, with this new definition, I want to show that this holds. In other words, when we plug these formulas, these new formulas we found, into our formula for the unit hyperbola, it should equal 1. So let's discover that together. So we have cosh squared of x cosh of x squared minus sinh of x squared. We hope that this equals 1 in order for our definition to make any sense. Well, let's find out. This is going to be e to the x plus e to the negative x squared, all divided by 4, plus e to the x minus e to the negative x squared, all divided by 4. A little bit of, let's see, algebra will show you this. E to the 2x, let's see, I have twice the product of these, so that's going to be plus 2 plus e to the minus 2x. And I already have my common denominator of 4. And then here it looks like I got plus e to the 2x. Oh, I accidentally changed the minus in here. I keep doing that. This should be a minus, you guys. You probably knew that. So that changes this to a minus as well. I was noticing that I wasn't going to get what I wanted. Okay, so e to the e to the 2x minus 2 plus e to the negative 2x, all divided by 4. This is the same thing as, okay, so we got e to the 2x plus 2 plus e to the minus 2x minus e to the 2x plus 2 minus e to the negative 2x. Again, our goal is hopefully this all simplifies to 1. Oh, nice. Those guys cancel. Oh, shoot. These guys cancel too. And we have 4 over 4. Yeah, nice. That's 1. So this works with our old definition. Now I wanted to kind of discover what the heck the derivative, let's do the derivative with respect to x of maybe the cosh of x. Notice that the original trigonometric functions had a nice cycling behavior. The derivative of sine was cosine. The derivative of cosine was negative sine. Let's see if we get something pretty like that for taking the derivative of this hyperbolic sine or hyperbolic cosine. We have d over dx of, let's see, e to the x plus e to the negative x, all divided by 2. But you guys, that's an easy derivative. This is 1/2 times the derivative of e to the x plus e to the negative x. We have to do the chain rule. We just discovered what the derivative of e to the x is. Is that fancy function that is its own derivative. So the derivative of this first part is just going to be e to the x again. And then the derivative of this second part, I have e to the power of some function. So I'm going to start with simply adding e to the power of that function. But then I have to multiply that by the derivative of the inside function. My inside function in this case is negative x. The derivative of negative x is negative 1. All right, so this simplifies to e to the x minus e to the negative x, all divided by 2. Oh, shoot, guys. The derivative of cosh of x is sinh of x. That's the other function. That's kind of nice. Homework, quote unquote, show that the derivative of sinh of x is equal to cosh of x. Okay. And also you should ask, wait, what about like tanh of x and things like this? And indeed, those exist. And of course, we expect definition. Tanh of x is the same thing as sinh of x, by definition, divided by cosh of x. And it has interesting behaviors as well. So the big thing I wanted to say we've just discovered, just by messing around with these hyperbolic functions, the derivative of cosh of x is sinh of x. Here's your homework assignment, not hard. The derivative of sinh of x is equal to cosh of x. And of course, we have all of these other functions. And I wanted to kind of list some results. I had them here, just so you can kind of show them on your own. Other results that you can show just by definition. We won't have time in these videos. I will show some things. So basic facts are this. This is absent of calculus. Cosh squared minus sinh squared of x is equal to 1. There are double angle identities that you can easily show. For instance, sinh of 2x is equal to 2 times the sinh of x cosh of x, just like the trigonometric counterpart. There are plenty of other things. Here, let's see. Just like in trigonometry, most things kind of spurs from double angle identities. So we also have those not double angle identities. I mean addition and subtraction identities. For instance, we can show that sinh of x plus y is actually equal to sinh of x cosh of y plus sinh of y cosh of x. So that looks a lot like the addition identity in trigonometry. You might ask, well, I wonder if the other one, oops, that's supposed to be x. I wonder if the other one matches, and it doesn't actually. So the cosh of, well, it doesn't perfectly match, of x plus y is actually equal to, we might even like this one a little bit more. That's going to be cosh of x, cosh of y, plus sinh of x, sinh of y. Notice that in the trigonometric counterpart, you always have to swap the addition in the middle. So here's some facts. And of course, if you know this one, then this one is easily derived. That's why I feel like this one's probably a little bit more important to show. Other things that you might discuss in trigonometry are inverse trig functions. Here, I wanted to list other things like just other facts. So let me get 3 more. The derivative of sinh of x is equal to cosh of x. The derivative of cosh of x is equal to sinh of x. It's a little bit prettier than the trigonometric functions. And of course, I could say something like this. The derivative of tanh of x is equal to sech squared of x. And that, again, looks just like the trigonometric counterpart. But I wanted to talk about, just like trigonometry has inverse functions. It's kind of funny because we're technically gonna talk about inverse hyperbolic functions before we talk about inverse trig functions in this class, but that's okay. What about sinh inverse, or maybe cosh inverse? All right, well, how do you find inverse functions in general? What you do, so I know that sinh of x is equal to e to the x minus e to the negative x, all divided by 2. And I can name sinh of x y. And I don't know if you remember, the whole process for finding inverse functions is you switch x and y and solve for y. So let's try doing that. That way we can find maybe some sort of, our goal is to figure out what sinh inverse is. We want to find that out. So how do we do that? It's this process, same process that we've done before. E to the y minus e to the negative y, all divided by 2. Okay, I want to get y by itself. This looks gnarly, so let's see if we can do something. I don't know, maybe multiply both sides by 2. 2x is equal to e to the y minus e to the negative y. Okay, but I want to remember that another way to write this is e to the y minus 1 over e to the y. That's simply exponent rules. Now what I'm going to do is multiply both sides by e to the y and hope for the best. I think something nice is going to happen. So here what I got is 2x times e to the y, and that's going to equal e to the y squared minus 1. All right, bringing things around, I think what that says is 0 is equal to e to the y squared minus 2x times e to the y minus 1. Okay, so you're probably thinking to yourself, well, what the heck is your deal with writing that in red? Well, what I'm noticing is that this is a quadratic in e to the y, so we can use the quadratic formula. E to the y is equal to negative b, so that's 2x, plus or minus the square root of, let's see, b squared, so that's going to be 2x squared, 4x squared, minus 4 times a times c, so that's going to be plus 4, all divided by 2. Okay, let's see if this simplifies. It sure does. We have 2x plus or minus 2 times the square root of x squared plus 1, all divided by 2, and that is equal to x. I'm actually going to get rid of the negative. You might ask, why can you just boot the negative? Well, I have e to the power of something. E is always, or e to the power of anything is going to be positive. This is an exponential function. There's nothing you can plug in for y to make this a negative value, so I think this simply equals x plus the square root of x squared plus 1. All right, so I want y by itself, though. So overall, here's what I got. E to the y is equal to this thing, but remember that fundamental relationship. E to the star is equal to square. We went over this in the I think the last 2 videos. If and only if star is equal to the natural log of square. So I have something like this. It looks like my y is kind of like my star, and this huge nastiness is kind of like my square. So what I get is y must be the same thing as the natural log of x plus the square root of x squared plus 1. And here we go. So this is my inverse function. Absolutely crucial. Notice I need the absolute value because of the domain restriction on the domain restriction on the natural log. Okay. Okay, crucial. Give me 1 second. I think the last thing I want to do in this video is just take this guy's derivative. And let me think about why this is... Do I need the absolute values on sinh of x? So this is my inverse function. Sinh... Oh, can I do that? Oh, okay, so check this out. Sinh inverse of x is equal to the natural log. I think this thing is always positive. This thing on the inside is always positive. Think about it like this. The square root of x squared plus 1 is going to always be greater in magnitude than the x. And I'm always adding this greater thing than... okay, so here, like this. Oh, shoot. What would be the best way to explain this? This is definitely true. X is always less than the square root of x squared plus 1. But that means adding x to both sides? No. Because I want to make sure that this thing is always positive in here. This is always true, no matter what. So I also have this. Negative x is less than square root of x squared plus 1. Both of these are simultaneously true. Huh. Okay, so adding x to both sides in this case gives me exactly what I want. But adding x to both sides in this case gives me 2x is less than x plus square root of x squared plus 1. I guess I just have to break x into the positive case or the negative case. So if x is bigger than 0, if x is bigger than 0, this still holds. Okay, so this implies that negative x is less than 0, which implies that... Oh, and 0 is less than the square root of x squared plus 1. This is always a positive quantity. So what we have is adding x to all sides here. It looks like I got 0 is less than x, which is less than x plus x squared plus 1. Okay, so this is positive in that case. What if x is less than 0? Well, 0 is certainly less than... Well, that means negative x. Oh, yeah, I think we can do this. If x is less than 0, that means negative x is bigger than 0. But I want to show that negative x is less than, still less than x squared plus 1. And I can do that like this. Negative x squared is equal to... x squared, which is less than x squared plus 1. Taking square roots. In this case, is going to hop back the positive square root. And the positive square root is negative x in this case. So taking square roots, we have negative x is less than the square root of x squared plus 1. And therefore 0 is less than... Okay, sweet. In either case. So if x is less than 0, x plus x squared plus 1 is positive. If x is bigger than 0, then this is still true. In other words, in all cases, this is true. Okay, so why am I rambling? I didn't plan on rambling like that, but I wanted to think about if I really needed this absolute value in my definition here. Turns out you don't. Always a positive quantity. Okay, last thing I want to do is take this guy's derivative, just to kind of get a little bit used to sort of the calculus here. Sinh inverse of x. And this guy's derivative is actually really pretty. So this is going to be the derivative with respect to x of the natural log of x plus the square root of x squared plus 1. We know how to take the derivative of the natural log. That was this week's theory video. So that's going to be 1 over x plus the square root of x squared plus 1. But then I have to multiply this by the derivative because of the chain rule. All I'm doing is the chain rule with respect to x of x plus the square root of x squared plus 1. Okay, that's equal to 1 over x plus the square root of x squared plus 1. Then I have to take the derivative of this part. Okay, so that's going to be 1 plus the derivative with respect to x. I'll show all work in this case. Square root of x squared plus 1. For this guy here, I have an outside function. It's this square root function right here. I have to take the derivative of that part. So this is equal to 1 over x plus the square root of x squared plus 1 times 1 plus 1 over 2 times the square root of that inside function, x squared plus 1. But then, of course, I have to multiply this, because of the chain rule, by the derivative of that x squared plus 1. And we're almost done. So again, this part right here is the derivative of the yellow function, evaluated at this inside function. I did not change the inside function because of the chain rule. So this is the same thing as 1 over x plus the square root of x squared plus 1 times 1. Plus, it looks like I have the derivative of x squared plus 1. This is just going to be 2x divided by 2 times the square root of x squared plus 1. That's kind of nice. These guys cancel. Finding common denominators, and here's where the magic happens. I'm going to multiply this 1 by, or I'm going to rewrite 1 as the square root of x squared plus 1 divided by the square root of x squared plus 1. And here's what we got. So I have 1 over x plus the square root of x squared plus 1. Over here I have the square root of x squared plus 1 plus x, all divided by the square root of x squared plus 1. That's after finding common denominators. And look at how stunning this is, you guys. Those guys cancel. And I have that the derivative of the hyperbolic sine is the square root of x squared plus 1 over the square root of x squared plus 1. Those of you guys psyched, I really, really encourage you to discover other things like the derivative. First of all, find a formula for cosh of x. In other words, homework. Show that cosh inverse, oh my gosh, cosh inverse of x can be written as the natural log of x plus the square root of x squared minus 1. And there is a domain restriction here. X has to be bigger than or equal to 1. And then also show that the derivative with respect to x of cosh inverse of x is equal to, I don't memorize it, so I have to look it up. Here we go. Oh, pretty. 1 over square root of x squared minus 1. And you guys, these are, unfortunately, this is one of those videos for those of you in STEM. These will come back ex machina, and they will save the day many times in the future. So I'm not just arbitrarily computing these results. These are very useful results. So getting used to these hyperbolic functions, really, really important. Again, their applications are everywhere. And they're kind of fun. They got some sweet, sort of pretty properties.